So this is the third session for the day, and David would take it.
Thanks for joining. I'm David Masip. I'm data science manager in Globo. Globo is a food delivery company based in Barcelona, and I'm going to talk about cluster experiments, which is a library that we've developed to design and analyze A/B tests. It's an open source library, so yeah, you can use it if you get something out of this session. These are the topics that we're going to cover. I'm going to start with an A/B test refresh. We're going to talk about experiment design and the libraries that can be used for experiment design. And I'm going to do a demo on the library I'm presenting today. A question, who is familiar with A/B testing? Who has run an A/B test before? Okay, good. So I guess there are two speeds in the session. I hope you get something out of the session if you've never run an A/B test, and something that if you're very familiar with that. So for the other half of the session, you may be a bit bored, or but I hope you get something out of the session. So I'm going to start with the A/B test refresh. So I'm going to start with a simple example that I'm going to be referring to during the talk, which is these very annoying upsell things that companies do. So you have something in your cart, and when you are about to buy, there's this, do you want something more? And this is the feature that engineers have developed, and essentially what is being asked to the data team is how to measure the impact of this. No, does this bring incremental order value? Does this lose conversions? These are the typical things that business would ask from a data team. And in general, the best way to answer this question is to run an A/B test or experiment. And these work in the following way. You split the population randomly. So you have some users that see this upsell banner, and some users that don't see the banner. So this is what we usually refer to, users in B are exposed to the treatment, and users in A are exposed to control. Then you run the test, you collect data from users that saw the variation, and users who saw the control, and in the end, for a given metric, you run an hypothesis test where your null hypothesis is that you didn't change anything, and you're collecting data in order to invalidate this null hypothesis. No, and you're typically, what people do is reject this null hypothesis when there's strong evidence that B is different than A, and this is typically done via p-values. If the p-value is very low, it means that you're probably wrong in your null hypothesis. No, and this p-value of less than 0.05 is the same as saying your false positive rate is going to be 5%, which means out of 100 times that you didn't do anything, that you tested a placebo, in 5 of them you're going to say that you have something different, whereas in reality you didn't have anything different. So this is the general setting for an A/B test. You split the population, and you measure in A and B, and reject if you see big differences. No. Then before running the test, actually what you need to do is design the test. And one of the big questions that people have when designing an A/B test, there are a ton of things like, how many variants do I choose? Which metrics do I measure? But one big thing is how long should the test be? No. And actually, this how long, there are like different variations of this question that are not related to length, but to decisions about how many users for how long, and these are the typical questions that would come. No? How much traffic should I put to B? People tend to do 50-50, but if it's a risky feature, you might want to do less. In how many geographies should my test run? Which should my type 1 error be? And then more advanced topics like, should I use variance reduction, or should I stratify my treatment allocation, which is out of the scope of this talk. No, but in general, people have all these questions before running the test, and typically the way to answer some of these questions is via this minimum detectable effect. And in general, what happens is that the longer the experiment, the smaller the test you're able to detect. And this is something that you're interested in general, to be able to measure very small effects. Even if your feature has a 1% increase on the metric, you want to be able to measure it. And in general, the longer the test, the smaller the effect. But also, you don't want to run very long tests, because then you get to test less things, no? And in general, the question of how long should the test run is answered via this minimum detectable effect. And typically, what people do is they agree with their business counterparts what effects are they interested in, and this can come up in a conversation like, are you interested in changes of the metric of 0.1%? And if they tell you, hey, no, this is too small, I'm not very interested in. But if you ask them, a change of 2%, is that interesting to you? And they say, hey, yes, for sure, I want to know if I change my metric at 2%, then it's a signal that your MDE should be in the range of 2%. No? And in general, you take these lines that I'm going to show how to plot them, but essentially you take these lines that have the dependency of length and minimum detectable effect, or MDE. You pick the change that you want to measure, you project it to the x-axis, and you get the minimum duration of the test. No, and this test, if you want to measure an effect of 0.25, you need at least 15 days of test. No, and this is how typically this is done. This is called power analysis or MDE analysis. I'm going to refer to both things indistinctively in the rest of the talk. And the rest of the talk is going to be about how to draw these lines. So now I hope it's clear that once you have this line, it's easy to decide the experiment length. Now what we're going to focus on is how we can draw these lines. And actually, there are different ways of doing it. Like, the first one is using online calculators. So you Google minimum detectable effect in Google, and you're going to come across these web pages that they have some inputs like number of visitors and your baseline conversion rate, and they give you an MD. It's then your work to translate this into experiment length, but they work for these cases, and you don't need to know how to code. No, so this is good. The only issue is that they typically only work with binary outcomes, so essentially conversions, but there are very relevant metrics like order value in the example that I was giving, delivery times, something that is very common in logistics, or profits, something that is very relevant to every company, that these tools don't cover. So the issue with this is that it's a bit limited in the scope. Then you can use stats models. It's a very famous Python library, and this is just ChatGPT telling me how to do this with stats models. So don't pay a lot of attention. But the thing that you need to understand here is that stats models require some inputs that are not always super straightforward to get. So essentially, they are asking you the standard deviation of the outcome and the minimum detectable effect, which is very common, and it will give you the required sample size. And this standard deviation of the outcome, for someone who's not very technical or doesn't know a lot of statistics, it may be a hassle. And then the library that we are presenting today, and we're gonna demo. So the difference in here is that you give a data frame to the library. So essentially, you collect some historical data before the experiment, you instantiate the class from the library. I'm going to explain later why we instantiate it like this. And then the library gives you these timelines, which is essentially this line that I was showing before. This is the output of the library. So in here, what you need to notice is that the input output of both libraries is slightly different. In stats models, you need to include the standard deviation, and it will give you the sample size. In these cluster experiments, you need a data frame with historical data, and it will give you this mapping. And once you have this mapping, you do what I told you before, essentially pick an effect and return the experiment length. So I guess there's an argument that stats models has a more simple input. One argument for the data frame input is that whenever there are like the two phases of the experiment, first when you design and then when you run the analysis on experimental data, the work that you do on the experiment design, on building these data frames, like creating the queries and so on, is useful whenever you do the experiment analysis. Essentially, this library also has experiment analysis functionalities, and essentially what it expects is a data frame with the same shape, but also a column indicating the treatment of each user or of each unit. No? And so while this is a bit more complex than this in an object manner, it can easily be reused later. So there's some useful work for the future that you already did. However, the reason why we developed this library, it's not this input-output that we prefer the data frames. It's the amount of cases that its library covers. No? So in general, the example that I showed in stats models, you're going to see that it has this TT in solve power. Essentially, what this is doing is telling you that this only works for a t-test. So basically, the main difference is that this stats models code that I shared only works for a t-test, and this library supports a ton more of things that we cared about in our use cases. No, so for instance, OLS, ordinary least squares, which is kind of equivalent to the t-test, but you can also add variance reduction to it, which I'm going to talk later. Generalized estimating equations, synthetic controls, and then cluster randomized and switchback splits, which is something that logistics companies run very, very frequently. And also it's easy to change the treatment allocation from 50 to 90% without knowing a lot of statistics. And also it's more extensible in the sense that if you have your own way of splitting the data or your own way of analyzing the data, the library can plug them with the things that already work in the library. No? So I guess the reason why we developed this is because it covers more cases that we were interested in. And yeah. And now I'm gonna do a demo showing how the library works. So this is a notebook that it's in the slides and it's public, and essentially this part is only the data generation part. So this is some historical data of customers, and this is order level data. So essentially you have one row per order, and for each order you have the customer, the age of the customer, the transacted value, and the delivery time, and then the city where it was delivered and a date of delivery. And so I've already loaded the data, and this is the hello world of the library. So essentially, you need to define via dictionary how you split and how you analyze the data. I was saying that there's a lot of ways to split and analyze the data. You need to be defining them. Then you need to tell the library, hey, this is the date column that I'm going to use for the analysis, and this is the target metric that I'm interested in understanding the effect. And this splitter and analysis, what they are telling you is you're splitting the data at the same, this non-cluster is at the same level than the data you have. So if you have data at order level, you're assuming you run an experiment at order level, and the analysis, it's you're running analysis with an ordinary least squares test. So essentially, this is what you are saying to the library, and this is a very weird case because you are splitting data at order level. For some companies, it doesn't make sense. They typically split the data at customer level. An example that could cover this is, imagine you're doing an experiment in logistics. So you're sending traffic to a logistics provider or another and seeing how they do in their cancellations and their delivery times. And you could do an order level experiment. But typically companies like to experiment at customer level to have a consistent experience for the customer, which we're gonna go later, but this is just a thought example. And essentially you ask this class to calculate the timeline, and you tell which is the statistical power that you need, and you tell the library some experiment lengths, and it gives you this line. So essentially what this line gives you is the dependency of the MD and the experiment length. And if you pick an MD of 3, this essentially means that if you run the experiment during 7 days, it's enough to measure your MD. So this is like the hello world of the library. It plots these lines, and we can get an experiment length based on the MD. Now I'm going to introduce the more advanced features of the library. So we said that companies like to split traffic at customer level, not at order level. And in this case, we are measuring something at order level, which is the order value. You can think of the upsell experiment. You're splitting, some customers see the banner, some customers don't see the banner, and you want to see on average if they are ordering more. No? So you're measuring this order value. So this t-test, or this OLS or a non-cluster split, doesn't work anymore. You are splitting in a cluster manner, and you need to tell it, hey, I'm splitting based on customer ID. So essentially, some customers are going to go to treatment, some customers are going to go to control, and it's not anymore an order level split, it's a customer level split. And because you are splitting at customer level, the regular OLS method doesn't work anymore, and you need to run a different analysis method to account for the fact that you split at a higher granularity. And then the regular inputs, which is the time column and what we are measuring, which is this order value. No? And if we run this, I run it with less days. What you see is that the experiment length is way bigger. It's like 21 days. And the reason for this is that in general, when you split at a higher granularity, like customer instead of order or city instead of customer, your MDs are going to be bigger, and you're going to need more data. And this is just a statistical thing that you need to deal with. Okay, so yeah, this is the two hello world examples. First, something that could be done with stats models, and then something that stats models doesn't handle well, which is this clustered splitting, which is something very common. For instance, in the upsell experiment, if you try to measure an order level metric, you would face this issue. Then something that people do in order to reduce their minimum detectable effects is variance reduction. And in general, the t-test or the ordinary least squares do something like this. You run a regression with a single covariate, which is the treatment, and you measure how big is this beta 1. This beta 1 is essentially the estimation of the average treatment effect, which is the metric you're typically interested in. And this is what the basic method does. However, if you want to do something a bit more complex, but that can help you have lower MDEs, you can apply variance reduction. And this variance reduction, it's essentially adding a covariate that is a good predictor of the final metric, and it's not impacted by the treatment. So essentially, if customer age is a very good predictor of the order value, then you're going to have lower MDs, which is something that you're always interested in. And this is a blog post from Facebook, from Meta, sorry, that they showed how do their confidence intervals look whenever they apply variance reduction or not. And you see very big confidence interval when they don't apply variance reduction, and smaller confidence intervals when they apply variance reduction. And typically, low confidence interval means low MD. Yeah, so I have a couple of examples of this. And essentially, we are doing the same experiment that we were doing before. So we split at customer level. We want to measure the order value, but the library allows you to add a list of covariates. And in here, I'm adding the customer age, and I already made the data where the order value is predictive of the customer age. So in this case, we're going to see a big effect. And in this case, you see that the experiment length goes from 21 originally to 7. No? So in general, whenever you have a good predictor of the outcome, you're able to reduce your experiment length. And how do you build a very good predictor of the outcome? You can use this technique called QPAC, which is essentially fitting a machine learning model, a supervised model, that predicts the order value and adding this as a covariate. And this is something that the library also supports, and I'm going to show you how it supports. It's a bit more cluttered, but it's also doable. So in this case, the way this QPAC works, you don't want to overfit your data, so you need to split in experimental data and pre-experimental data. So you're going to use the pre-experimental data to feed your machine learning model, and then the experimental data to run the analysis. No? And keep in mind that this is happening at the design phase, so you don't really have experimental data. So essentially what you need to do is to split your pre-experimental data in two, like a pre-experimental data and a pre-experimental data. And this is what we do here. We take data before February as pre-experimental data, and data after February as experimental data. You're going to see that I was using dictionaries all along before. In this case, because we need to pass an object that is not a string or a float, the way the library currently works is that you cannot instantiate these classes with dictionaries. You need to instantiate via classes and an object composition in the end. However, if somebody wants to modify the library so that this can work with dictionaries, I'm super happy to see a PR. And here you see a bit more of clutter. So essentially, we need to define the splitter, which is comes from the library. We need to define a way to analyze the data, which is this clustered OLS. This comes from the library, and you need to instantiate this normal power analysis that has a splitter and analysis, and then it has these two things, which is a QPAC model and some features of the QPAC model. And yeah, so essentially what this will do is we will fit a model with pre-experimental data on these two features, and then predict using the experimental data. You see here we change the covariates to this estimate of order value. This is something that will come from this, will be handled by this Kupak model attribute in the class. And this is how we do it, and typically it takes a little longer. I also run a richer experiment length, but you see that the MDs have gotten smaller, and in the end we end up with an experiment length of 5. So yeah, so we went from an experiment length of 21 without any covariates. We went down to 7 with a single covariate, and when adding this Kupak model, we went to an MD or an experiment length of 5. So in general, this is with fake data, but you're gonna see some drops in experiment length when you apply these techniques. And then the thing that I was saying before, that we can use all of this that we did in the experiment design for the experiment analysis. So this is also a thought experiment. Let's imagine that our experiment started on March and was like 3 weeks long. And here we need to store some real pre-experimental data because we're going to use that for Kupak. And here we've essentially simulated a couple of effects. We've simulated an effect of 1.5 in the order value and an effect of 0.2 in the delivery time. So here we already have our experimental data that has the same schema as before, but it also has a treatment column, and the library allows you to analyze this. And you need to import other classes, but as you can see, the analysis type is the same as before, and there's this analysis config that works in a very similar fashion as before. In this case, you need to define a couple more things like metrics and variance, and which is the variant column. But in the end, it works with the same classes, so it's a similar syntax. We've also added a dimensions thing here, which is we want to analyze all the data and also New York and LA separately, but this is not something super important. And so we run the analysis with the experimental data, and we see some estimations of the average effect. So in this total dimension, this is all the data, and we see an effect estimated of 2.4. The real effect was 1.5, so it's not a great estimation, but you have a confidence interval that covers this, and it's a pretty wide confidence interval. So in general, whereas you're sure that there's some effect that is not 0 or quite sure, because the p-value is low, you don't have a lot of confidence on what this value actually is, because it could either be 0.3 or 4.5. And then we can replicate what we've been doing before. No, we can add covariates, and it's as simple as adding these covariates in the analysis config. And we see that with the customer age covariate, the average effect is not great either. And finally, what we can do, and here again it's more cluttered because it doesn't work with dictionaries, but it can also be done in the library. We can add this Kupak model, and we can analyze using the real experimental data and then the pre-experimental data to train the Kupak model. And in here, the average effect that you estimate is closer to the original effect that we simulated, that it was 1.5. So we went from 2.5 to 1.8, and the confidence interval, you see that is now smaller. So you have a narrower range of values where you think the average effect is. And this is it. So what I talked about today is that cluster experiments allows you to run MD analysis based on data frames. It has many more use cases than stats models, including variance reduction, and you can easily reuse your design workflows to experiment analysis. we are looking for contributors. You can see we have a ton of issues that are open. There's a link to the notebook in here, and we are also hiring in Globo. So if you want to join, talk to me. And I guess this is it. So thank you.
We are now taking questions. Is there anyone who has?
Hello. So I imagine in the real world data, there are going to be a lot of rows, right?
A lot of rows, yeah.
Yeah. So if the data doesn't fit in the data frames, what would you do in this case?
So the whole library assumes that you can fit data into a data frame.
Okay.
It currently works with pandas. One thing that we could do is go to a more efficient library like Polars. I think what people with lots of data, what they typically do is they run everything in SQL, but also there's a trade-off in here that you cannot easily do variance reduction with a lot of complexity, no? So I think Meta and these kind of companies do everything in SQL.
Okay, thank you.
Any other question?
Is there in your code a way to show in more verbose way or more explicitly how these calculations were done? What do you mean? Uh-huh. Mm-hmm. Okay. Okay, so I guess there are methods in the main class that give you as an output standard errors uh, of a given data set and a given metric and a given analysis method. So I guess what you can do is if you wanna like debug this or understand more where all the calculations are coming from, is calling these raw methods. In the end, this MD timeline is a wrapper on top of these standard error calculations that runs through different experiment lengths and so on. No? So I guess my advice would be to go to the methods for standard errors, which is the closer that you can get if you don't want to go to the stats models call, which is this I think it's harder to interpret.
Rates or something like that? And why not bootstrapping?
Why? So which kind of metrics did you say?
Click-through rates.
No,
any
yeah.
ratio metric, like.
Yeah, click-through rate. It's theoretical. It's handled by cluster OLS. So whenever you do an experiment based on customer level and you want to measure the click-through rate, this is the typical case of cluster OLS. You can also do it with Delta method that is also in the library, and bootstrapping is not in the library. It can be added. The reason why we don't typically do it is because it's slower. So yeah, but if you want to add it, happy to take it.
Okay.
Anyone else? All right. Thank you so much, David.